Hey guys, Greaves here. Last lesson we were talking about photons and energy and stuff like that. So one of the ways, right, that we can find the energy associated with light, right, is this little equation right here on the reference table, right? Energy of the photon, right, it's going to be equal to HF or HC over lambda. Well, remember, the reference table gives us the spectrum, electromagnetic spectrum, and it gives us frequency or wavelength, right? So, if I have the frequency, I can find the energy. If I have the wavelength, I can also find the energy, right? But now I want to get real specific about something. We had talked about that business as energy is quantized, right? And what does that mean? It comes in these discrete bundles or packages. Remember the little analogy of a stair, right? I can't be hanging out in the middle of a stair, right? If it's 1 foot, I can't be 1.5 feet above the ground, right? It only comes in 1 foot, right? I could be 1 foot, 2 foot, 3 foot, 4, etc., right? So how does that relate to energy that's given to us by, say, the sun? Well, let's take a look, and let's take a look at what I mean by this energy business is quantized. Okay, so I'm going to be specific, and we're just going to stay with, if you look at your reference table, you're going to look at something that's called an energy level diagram, where the regions gives us two, hydrogen and mercury. Okay, let's just concentrate on hydrogen for right now. And it's a little strange because we're representing where we're trying very hard, this diagram is trying very hard to represent where a electron can be when it's in the hydrogen atom, right? So let's just take a look at here for a second. It's called an energy level diagram. So let's take a look here. What is this saying? All right, ground state. Right? It's very hard, guys, when we're not together. I get it, right? So I'm trying very hard to kind of do my best here. So suppose I have a hydrogen atom. Let's draw it out, right? So let's suppose I have a hydrogen atom, right? So here's the nucleus, right? And what am I going to have in hydrogen, right? So I'm going to have an electron, right? Which is going to be orbiting. Now, if you can remember from chemistry, what can happen, right? I can get this electron, right, to go, right, move to another, say, energy level, right? I don't remember what you called it in chemistry, like which shell. Think of these as the shells, right? Remember, right? And what we call them here in physics for this particular hydrogen, right? We say this is going to be n equal 1. So left, where does the electron want to be? Well, it wants to kind of orbit, right? The hydrogen atom, right? At this little n equal 1 state. And that's really where it wants to be. However, suppose I give, right, this electron some energy. What's going to happen? Well, it is going to get excited. Hopefully that kind of rings a bell from chemistry. And it's going to go to another energy level. Call this n equal 2. Then what? I give it more energy, n equal 3, 4, etc. Right? And we can go all the way out to n equals 6, and after that, it's gone. Okay? So these would be like the circles, right? Or the states that it would be in outside of hydrogen, right? N equal 1, n equal 2, 3, 4, etc. But we don't want to draw this on a piece of paper. So what we've done is we've come up with another way to represent this, and I'm going to redraw what I have here on the reference table. Okay, so here is my ground state, right? That's where my electron would be, right? N equal 1, right? That's where it wants to be. However, suppose I gave it some energy and I kicked it up to n equal 2, right? We could do that, right? So I could get this electron at the ground state to move up, right, to n equal 2. All right, and now this is where this business of things are quantized comes in. And what that means is energy only comes in discrete bundles. It's not continuous. It's either this value or nothing, just like this stair analogy. Okay, so now let's go back here for a second and let's look at the reference table. So what can I have? Well, I can have an atom, right, the electron at the ground state, and I can I can give it some energy. I can go to 2, 3, 4, 5, 6, and then infinity. We're going to talk about what that means in a second. Okay, so just think about this as the circles, right, around the outside of my hydrogen, right, that it's orbiting. Okay, better way to kind of represent this. All right, so now over on the right hand side, so this are my levels, energy levels, 1, 2, 3, 4, 5, 6. This is the energy. Okay, so what about energy? All right, so now it's going to be a little strange. I notice I have an energy of 13.6, and it's electron volts. We're not going to worry about it too much. Just remember from electricity that electron volt is that small unit of energy. It makes more sense to use electron volts in this particular case because it really is one electron moving around. Okay, so I'm going to go from minus 13.6 to a minus 3.4. Well, what's happening here? Believe it or not, it's getting, how do I put this? Less negative, until I get to what? 0. So what happens when I'm at 0? Well, when the electron has 0 energy, we say that it's ionized. I'll talk about that in a second. But let's figure out, let's go back to this quantized business about energy. Specifically, what type of energy is the hydrogen atom allowed to emit or absorb? Which I mean is, it's quantized. Energy from all the elements, hydrogen, mercury, whatever, it's quantized. It cannot accept anything. It's predetermined. Nature has already predetermined what values an atom is allowed to absorb or emit. And by the way, when it absorbs energy, it's gaining a photon, right? A packet or a bundle of waves. When it drops down, what does it do? Lo and behold, it emits a photon, a package of energy. And by the way, sometimes, right, it's light, sometimes it's IR, UV, microwave, whatever, but sometimes it happens to be in the visible spectrum that we might be able to see. All right, so let's take a look and let's see how I go about calculating some of these values. And let's talk about what I mean. And hopefully you're really gonna grasp what this quantized business means. All right, so let's say that from our reference table, at the ground state, right, it needs, and this is really what it's saying. So an electron that's at the ground state in hydrogen needs 13.6 electron volts to become ionized. That's what we say, right? To take the electron and rip it away, to ionize it, it needs 13.6 electron volts. Well, let's see if I can get this to go up to n equal 2. And if you look at your reference table, it tells me that it needs, right? So it's just telling me at this state, it needs 3.4. We're going to do one more. I'm just going to do one more, right? So this is going to be minus 1.51 EV. This would be n equals 3. I'm not going to do the rest of them. We'll just leave it like that, okay? So let's pose a question. Hey, if an electron is at n equal 1, how much energy must it, and by the way, absorb? In this particular case, think about this. It's getting less negative. Less negative means it's gaining energy, right? To go from n equal 1 to n equal 2, right? So how much energy do we need? Well, we know that it has to absorb a photon, so we say energy of the photon in this particular case. Now I'm going to go back to the reference table for a second just to show you, because we have two ways. There are two ways to find the energy of a photon. Well, if I know the frequency or wavelength, however, I can find it from my energy level diagrams. And the energy of the photon in this particular case is going to be given by E initial minus E final. Right, so let me write that down. E initial minus E final. Where this is going to be where I started, and this is where I ended. So believe it or not, it really is just as simple as this. So I want to know, I'm going from 1 to 2. How much energy do I need? Energy, where did I start? Minus 13.6 EV minus, a what? Minus 3.4 EV. So let's do a little bit of math. This is a minus and a minus, right? So it's a plus. So I get 13.6 minus 3.4. Lo and behold, it's minus 10.2 electron volts, right? Right? So what is this? What are we saying? For this electron to go from n equal 1 to n equal 2, it must absorb that much energy. Now, don't be too confused or worried about the pluses or minus. How do I know this is absorbed? Well, there's two ways to look at it. I'm going from 1 to 2. The only way to go from 1 to 2 is to gain energy. I absorb it, and believe it or not, the negative sign here is an indication that it absorbs. Is that okay? All right, so going from 1 to 2, I need to absorb 10.2. Now, here comes the weirdness of the universe. Suppose I hit this with, just suppose, right? I hit it with energy of 10, I'm going to make it a negative, 10.1 electron volts. What happens? I'll give you a second. Well, the answer is nothing. Nothing happens. Why does nothing happen? Because energy in the hydrogen atom and any other atom for that matter is quantized. It can only absorb or emit predetermined values of energy. So 10.1, well, what happens? The answer is nothing. Right? What happens is the electron stays at n equal 1. What happens if I hit it with, suppose, right, energy of, let's make it minus 10.3, right, 10.3 electron volts. What happens? Well, you guessed it. Nothing. Why? Because in my stair analogy, that means I'd be hanging out just a little bit above this line. Can't do it, right? So this is an all or nothing game. It has to be the exact predetermined number, which we already know and figured out, or nothing happens. Is that okay? So this is why we say energy is quantized. All right, let's take a look. Let's just do another one. We're here already, right? So let's say, hey, how much energy must I absorb, right, to go from n equal 2 to n equal 3? All right, energy of the photon is equal to EI minus EF. So where am I starting? Minus 3.4 minus 1.51 electron volts, right? So lo and behold, what do I get here? Clear all this. Minus 3.4 plus 1.51. Oh, I did something wrong there. I gotta do a minus, right? Minus 3.4 plus 1.51, and I get a minus 1.89 electron volts, right? So the only way, right, for this, right, so let's just put this here. This is what? 10.2 electron volts. And the only way to go from here to here is what? 1.89 electron volts. How do I know? I am absorbing, by the way. Absorbed. How do I know? I went from n equal 2 to n equal 3, higher energy, right? Or this negative sign here. Well, since I only did 3 of them here, what's another one we can do? Let's go down. Let's go down. Let's shoot straight down from n equal 3 to what? N equal 1. All right, what happens in this particular case? Well, I am dropping down from a higher energy to a lower energy, And the only thing that happened there, it's going to kick out a photon, right? So E photon, E initial, minus E final. So what am I starting here? Minus 1.51 minus a minus 13.6 electron volts. Hopefully I did that correct. This turns out to be a plus, doesn't it? So minus 1.51 plus 13.6, lo and behold, I 12.09 electron volts. Now look what happened here. It's going to be a positive sign, which means it must what? Omit. In this particular case, it's going to omit a photon. So, this is pretty much energy level diagrams, meaning really hitting the quantum world, right? Meaning that energy is not continuous. It only comes in discrete bundles or packages, which, by the way, nature has already laid out for us, right? What else do we have here? So on our reference sheet here, well, I have Mercury. Look what we have. Now, Mercury, it's a completely different element, isn't it? So it's going to have a completely different set of energy level diagrams. Once again, it starts at ground state, but my electron can go up to a different levels. I don't know the answer to this, but energy and hydrogen, they say 1, 2, 3, 4, 5, 6. I don't really know why. Mercury, they do A, B, C, D. It means the same thing, right? Ground state, up 1, up 2, up 3, etc. And notice, once again, we're going to have a different values for moving from 1 to 2, or A to B, which is the same as 1 to 2, as in hydrogen. Now, one thing, I'm going to give you some problems on this as well, so you'll do a little stuff here. And it's exactly the same. It's just the difference, no matter what, it's the difference between the energy levels, right? And if it goes up, absorbs. If it goes down, it emits. Now, sometimes, right, if we're lucky, we might be able to see some of those photons. Most of the cases, we don't. One of the reasons why Mercury is here, I'm going to tell you now. Probably not here at your house, right? But back in school, right, we have all those fluorescent light bulbs. Inside the fluorescent light bulb is mercury gas. Why is there mercury gas? Because I have basically what's going to happen is we're putting an electric current through it. The electric current is going to hit into mercury. It's going to cause atoms, I should say, my bad, it's going to cause electrons in the mercury to bounce around continuously up and down from different energy levels. And mercury, by the way, just gives us the most, right? The most visible colors, the colors in the visible spectrum that we can see. So we're tricking our eyeball, right, to see a lot of red and blue and green and yellow. It's not a continuous spectrum, right? But the more colors that come in, the more our brain perceives it to be white light, okay? So this is the energy level diagrams associated with hydrogen and mercury. Real simple. Energy of the photon is E initial minus E final, right? And I'm going to give you some problems to do for a test visit on this. I think also I'll give you a little lab. It's actually one of those applets. It's totally pretty cool, and I think you guys are going to enjoy it. All right? Have a good weekend, guys.